Hello everyone, in this video we'll be discussing propositional logic. Now if you're wondering, a proposition is just a statement. So here we have logic about statements. So P and Q are statements. A statement we're assuming to either have truth to it or it's not true. So truth or false basically. So there's not a statement that could be true or false sometimes. In reality there are statements like that that kind of depend on whatever you're talking about. For example, someone can say they're the best player of chess in the world. And that may be true at that time, but then it may not be true later on, or they may think they are, but they aren't because they haven't met an opponent that has actually matched them. You kind of know what I mean there. But for us, it's either true or false. So if you have two statements, P and Q, there are actually a total of 4 combinations, because if P is true or false and Q is true or false, you have 2 choices for each of them, and 2 to the second power is 4. So we have true, 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 false, false, true, or false, false. And the way I like to think of this is you start with the first one, and you write true, true, false, false, and then for the second it's true, false, true, false. And in fact, if we had a third one before, there would be 4 T's, 4 F's, and then you just repeat this block below. And that shows you all the 8 possibilities. Of course, 8 there because 2 to the third is 8. And why is it 2 to the power? Because there's 2 possibilities for a statement, true or false. Now we get into these. We've actually spoken about these symbols before. We have and, or, and if then. So this is the conditional or implication. So we've seen that and statements are true when they're both true and false otherwise. So if they're both true, then this is true. Otherwise, it's false. Or means one of them was true. So in fact, all of these are true. The only time it could be false is if they're both false. So that makes sense. Now, if P then Q, we've actually seen before that truth can imply truth. Truth cannot imply false. So that's false actually. False can imply truth, and false can imply false. The false can imply truth we've actually struggled with before, but it's not too difficult if you know a very particular example. And a really nice one in math is that if you assume that 1 is equal to -1, which is a false statement, scoring both sides gives you 1 is equal to 1, which is a true statement. So assuming something false could give you something true. That's what that means. Okay. There's a little more to recall here. I'm going to create a new table. So let's say we have P. Not P is just reversing the truth of P. So if P is true, not P is false. If P is false, not P is true. We also have this double implication. Now, remember that there is what is known as the converse of a statement. So if you have a conditional, if P then Q, its converse is if Q then P. So a biconditional statement means that its converse is also true. So in fact, really this is equivalent, this is an equivalent statement to if P then Q and if Q then P. Okay. So this is what is known as if and only if, or biconditional statement. Now, it would be interesting to see what that would look like. So I'll actually include that here. Let's just, because it's kind of newer, let's include it in red. Doesn't really matter though, I guess. So P if and only if Q. So let's think about this. This would be true, so we have to kind of think of what this is doing. So I guess if you wanted to, you can create a column before this that's the converse of Q, if Q then P. And then take the end of those 2 columns to get this red one. Now I'm going to try to think of it simultaneously, but if P then Q is, if P and Q are both true, truth implies truth, and the other way around, truth also implies truth. So that's true. Now remember, truth cannot imply false, so that already is false. The other way around is actually true because false can imply truth. So going from Q to P, that is true. But taking the end of those 2 statements, false and true, is false. And very similarly here, though P to Q, that direction is true, the converse, Q to P, truth does not imply false, so that's false. Taking the end of a truth and a false is false. And false can imply false, so both ways that's true. So that's what the truth table looks like for a biconditional statement. Okay, now here we see these two statements are what are called logically equivalent. Now, logically equivalent is basically the whole point of this section. So we'll be discussing in a little bit of detail these equivalences. This is one logically equivalent, logical equivalence, but logically equivalent, I should say. Sorry, I'm getting my words mixed up. So that these two are logically equivalent. So I guess you could call it a logical equivalence or something like that. So we'll be taking a look at a few of those right now. They will often involve kind of manipulations of things like, let's say, a double negation, or maybe some type of relation between an implication and a disjunction, which is an or statement. So we'll see that right now. Okay, so actually, before moving on to logical equivalences, I want to take a look at this this example here. It's a pretty interesting example. It has to do with the game of Monopoly. But actually, without even knowing the rules of Monopoly, we can work our way through if this statement is actually true or not. So this is one entire statement. Now it's built and composed of other propositions, other statements. So we're going to essentially split things up depending on if we have ands or ors or if-thens. And then we'll try to call each of those different statements, P, Q, maybe R and S if we need to. Let's actually see. So I see if this, I don't see then, but it's kind of implied here actually. So if then. So if you get more doubles than other players in the game of Monopoly, then you will lose. So there's an implication of then here. There's an implied then, so I'll write that then. Then you will lose. Okay. Or, so there we go, so we have another different thing there. Or that if you lose, okay, if you lose, then, okay, so I've passed it then, you must have bought the most properties. I meant to put a you must have there, but that's okay. So we actually have a total of, I guess, 4 statements separated that I've underlined. With this first one underlined, then after that implied then, you have another underlined one, then one here, and then one there. So it's 4 total. But the you lose is actually repeated here. So let's do this. Let's let me see if I have a different color here. So I usually have them up in front of me, but that's okay. So I have P, I have a green here. So let's call this P. The you lose statement, we'll call that Q, so that's also Q here. And this last statement, you must have bought the most properties, we'll call that statement R. Now we have 3 statements here, 3 propositions. In other words, we have 3 statements that we know are either true or false. Then we're kind of combining those using or and a few if and thens. So in fact, if you just kind of combine this into like a short statement like we've seen in the past board kind of, we have P implies Q. That's if P then Q, or, so that statement, or if Q then P. Or sorry, if Q then R, sorry. So without even thinking about it too much, we've already broken it down to this kind of nice, I guess, symbolic statement instead. So I haven't even talked about what it really says. I just noticed that we have if-thens and ors, and I'm just calling those things, those statements, those propositions, P, Q, and R. And now we'll make a truth table, and we'll actually find out if our statement is true. If it is true, then we'll see a T all the way down, because it'll be true no matter what. Now, the funny thing here is that if you actually think about it, some of these statements are a little weird. Like, if you know the game of Monopoly, rolling a double just means you roll 2 of the same number, because you roll 2 dice at a time. Now, if you roll more doubles than other players in the game, doesn't necessarily mean you lose the game. Well, I mean, you have to know the rules of the game of Monopoly. But, I don't know, it's kind of hard to say because, again, if you know Monopoly, if you roll a double, you roll again. But you can only do that once. If you roll a double more than once, then I believe you go to jail or something. So rolling a double a lot is kind of not good. Okay, on the other hand, regardless if this statement is true or false, we have an or. So if this entire statement is true, one of them must have been true. Maybe they're both possibly false, in which case the or statement won't be false. So really what we're asking I guess, the only way this could be a false statement is if both of these could be false at the same time. So it's something to think about. Let's just create the truth table here and let's see what happens. So I have P, then Q, then R. Okay, then we're going to look at if P then Q. Then we're going to take a look at if Q then R. And then we're going to take a look at our actual statement, which is the OR of those two. Okay. Now remember, when you have three statements, 2 to the third is 8, so there's a total of 8 possibilities here. Let's see if we can do this justice. It's 4, 5, 6, 7. I think that should be 8. Not quite, one more. Okay, that should do it. All right. So again, the way you do it is you split the first one into 2 equal halves. The first half are truths, so that's 4. And the second half of those are false. So that's 4 truths, 4 false. Then you cut it into quarters. So we have 2 T's, 2 F's, 2 T's, and 2 F's. That should be an F, sorry. And then you have 1 of each, so TF, TF, just alternating like that. True, false, true, false, true, false, true, false. Perfect. So these are all different combinations. They're all true. The first one's true, the last two are false, and they're all different, of course. Okay, so let's look at if P then Q. So I'll ignore the R column for now. So truth can imply truth can imply truth cannot imply false, truth cannot imply false can imply truth, but both those are true, and also false can imply false. So there we go, just these two are false. If Q then R, so we'll now ignore P. Truth can imply truth cannot imply false. Okay, false can imply true, false can imply false, so that's true. And in fact, notice this TT, TF, FT, and FF are just the same repeated block as the previous 4. And I kind of mentioned that earlier. So I'm going to repeat this, TF, TT. Now what you notice is that none of these are both false. So the OR statement is always true. If true or true is true, true or false is true, false or true is true. That's true, and these are all true, actually. So in reality, in analyzing this a little more, just using these symbols, basically, and truth tables, this is actually a true statement all the time, without even knowing what it means, just looking at it and analyzing it. And in fact, a lot of people, logicians, people that study logic, do this. They look at statements that people make, they break it down symbolically, create truth tables, and see if the person has a logically sound statement or not. They do this for politicians, for example, or people that are in charge of companies, and just try to see if what they're saying makes logical sense. Also, you have people behind the scenes that are making sure that the people they're representing have statements that make sense as well. Now, of course, you know, in that sense, the public doesn't really think about it too much, right? Depending what the statement is and all that, they just kind of care about the actual, you know, what the person is trying to say, so to speak. But at least this is good to know, of course. Now, obviously, it has applications, and this is a pretty interesting example. But now we'll finally take a look at those logical equivalences I was talking about. So let's see that right now. Right, so here I have a list of a few different ideas that are all basically scenarios where you have equivalence, logical equivalences. So here, De Morgan's law shows this logical equivalence. It's basically a distribution of the negation. If you distribute negation amongst an and, you get an or with each of those statements inside that were anded together, but now negated. And similarly, if you distribute negative in an or statement, the negation distributes, but then you have an and of those negated statements. Okay, so that's kind of an interesting thing, and again, those are called De Morgan's law. So if you want to distribute a negative in or distribute a negation in, then ands and ors kind of swap. So just kind of think about that. And now if you want to actually prove this to yourself that these are indeed equivalent or logically equivalent, you can create a truth table. And if you create a truth table, they'll both give you the same, the columns will look the same basically. They're both true when the other one's true and false when the other one's false. I'm not going to do that, but you can try that. I'll actually show that for this one though. This one I think is a little more interesting. So here we can write implications as disjunctions. So as it turns out, the statement if P then Q is actually equivalent to not P or Q. And I think we actually spoke about this in an earlier video. But here I'll actually show this. Let me show it in red over here. So let's say we have P and Q. Try to squeeze this in. We have if P and Q, and then we're going to find out what not P or Q is. Okay. So remember how it goes: true, true, false, false, true, false, true, false, true, false, true, false. Perfect. Now we know the implication truth, so we know how that works. It's true when they're both true. True cannot imply false, but false can imply true, and false implies false. Great. But now what about this? It's a little more difficult to see, I think. But remember, we're taking the or of not P and Q. So just to remind us, not P, let me kind of try to squeeze it in before P here as like an extra column. It is opposite truth of P. In other words, it's false when P is true and true when P is false. Now, if you take the or of not P and Q, false or true is false. False or true is true, because one of them is true. False or false is false, because they're both false, neither is true. True or true is true, because they're both true. True or false is true, because one of them is true. And I'm looking at these two. Okay. And notice, we have the exact same truth table column for each of these, so we can say that those two statements are indeed logically equivalent, and I use this double-sided arrow to show that. Sometimes you could possibly use equality if you wanted to, but I'm just using this instead because I don't want to use that equality symbol. That equality symbol will be used for numbers, not for logical statements. Anyways, double negation, you can actually, I guess, pretty easily create a truth table to verify that that is true. Basically, if you negate something, it changes the truth of it, but if you negate again, then you get back to the same original statement as far as truth is concerned. So we say double negation is equivalent to the original statement. And now for this example, I'm going to simplify a negation of an implication. Now, the word simplify may be a little weird here because maybe this is going to look more simple than our answer actually. So the phrasing of simplifying that may be a little strange. Probably what we can say is find a statement that is logically equivalent to this. And that actually gives us kind of a hint because we know an implication can be written as a disjunction as we just spoke of. So this is logically equivalent to replacing the inside parentheses with not P or Q. And by De Morgan's law, this is equivalent to distributing the negation and the or becomes an and. So we have double negation of P and negation of Q by the second De Morgan's law actually. Notice or changes to and. And from this, double negation is just the original statement. So this is the same as P and not Q. It's pretty strange. But this is the final answer. So this is simplified. Quote unquote simplified. But that was a great example because he used all three of these. Okay, that's all I wanted to say for logical equivalences. The last topic I want to discuss here actually has to do with deductions. And the deduction is actually a very good application of propositional logic in the sense that you can actually use deductions to basically deduce things. I mean, it kind of sounds like what the word says, deduction. Essentially, you can conclude things assuming some statement is true. You can prove something else is true. So we'll see that right now. It's actually very useful. So we'll take a look at that right now. Okay, so here for deductions, this is the main, I guess, rule we'll be using. So I'll explain what this means right now in words, but I think it really helps to look at the truth table first. So let me create a little bit of space here and write the truth table for this. We've seen the truth table for this quite a few times already, so let's take a look. So we have P, Q, and then the implication, if P, then Q. Now I'm making it look like we're kind of adding these two to get this. That's what this reminds me of. You stack these on top and then the result is this. Now, of course, there's this kind of triangular symbol with these dots. This is just shorthand for the phrase therefore. Essentially, this is the result of assuming these to be true. Okay. So now looking at the truth table, let's see what exactly happens. And again, we've seen the truth table for this quite a few times, but let's just take a look. So we have TTFF and then TFTF. Okay, great. Now, as far as implication goes, remember truth can imply true, true cannot imply false, and the other two are true. Now, I said this in words earlier. Let me try to say this here. When these both are assumed to be true, true, then that implies that this is always true. Let me write always on top. In other words, when these are true, this must be true. Let's see if that's the case here. So when do we have a scenario where if P then Q is true and P is also true? That's here and here at this row. Notice any other row doesn't have both of these being true. And notice Q is definitely true when that is the case. So this is a correct result. So if you assume if P then Q, and you also assume P, then that means Q must be true. Which makes sense because this basically says, I mean, if you think about it, this basically says, assuming P is true, and you have the statement, if P then Q is true, well, I mean, the hypothesis is true, so the conclusion is true then as well. The book actually shows a pretty okay example of this, and it has to do with a child getting a cookie if she eats her vegetables or something like that. So the two statements I'm about to say are equivalent to this. So if the child eats her vegetables, then she gets her cookie. So that's a true statement. So the parent's not lying to them or anything like that. So they're going to stick true to that. And she ate her cookie, or if she ate her cookie, she ate her vegetables. Then the result is that she will get a cookie. Right? That makes sense. So again, the statement is, the if-then statement is, if you eat your vegetables, you get a cookie. So if you actually did eat your vegetables and that statement was true, then of course you will get a cookie. Great. So that makes a lot of sense, but with this table, I think it really helps. So here for this example, we want to show this is true, and then we also, after this, want to decide the validity of this deduction. So here, let's actually create a truth table here, and let's see. There's only two statements, so we're going to have a pretty kind of short one like we're used to. So we have P, Q, and then we have if P then Q, and we also have not P then Q. I need to have space there. Does that make it on the board? Yeah, great. Just making sure. I don't think I have room for not P, but we can kind of imagine what happens there. So T, T, F, F, T, F, T, F. Great. Implication we know like above is just T, F, T, T. Now what if you had not P, then Q? So just imagine these are negated. Let me write it in red. So F, F, T, T. So false can imply truth, so that's true. False can imply false, so that's true. Truth can imply truth, so that's true. But truth cannot imply false for this last one. So that is false. Okay. So if we assume that both of these are true statements, is it the case that the Q is also true? Well, I mean, yeah. So if you see here, these are the ones we're assuming to be true. That happens in these two columns, or these two rows, I should say, here and here. But notice also Q, what our supposed result is also true for each of those. So this is indeed a valid statement. So we have shown that assuming these two are true, Q is also true for each of those scenarios. Fantastic. This one is going to be actually a little harder to show because the truth table is going to be a little longer. I'm going to try to draw some of the truth table, and we may not need more of it actually. So let's see. There's a lot here, so let me see. Maybe I'll extend over here. So we have three statements, P, Q, and R. Okay, I'm just going to do the first 4. I think we have space for those at least. The board smudging a bit, but it's okay to follow something. Okay, so TTFF. I'm sorry, we're going to have TTTT. There we go. So I don't have space for the FFF ones, but we'll see if we even need them. If we do, I can move on to a separate board. But I think this is going to be okay. Let me just get away from that smudging. Sorry about that. Okay, so all true, and this is going to be true, false, or I guess true, true, false, false, and then this is alternating TF, TF. Great. So now we have the implications. Those are the new statements here. So if P then R, that's true. Truth cannot imply false, so that's false. Truth can imply truth, so that's good. And truth cannot imply false, so that's false. Okay, what about, well, I guess we need if Q then R, that's another new statement that we don't have already here in the truth table. So when you look here, this is just a normal TTFF block like we had there. So this implication is just going to be TF, TT. I'll let you think about that, but it's literally the same thing as that, just copy. But we also actually have something else needed here in this truth table, and that is P or Q. So P or Q is pretty easy here. P is always true, so this is always true. Okay. So what are we assuming? We're assuming these 3 here. This one, and this one. So here, these are all true, and the result is also true. So I'm going to circle it like that. So that's fine. Here, these are also true, and the result is also true. So actually, so far, it seems like it works. But we need to show that it would work for the scenario where P is false. So I guess I would have to write that now. So I'm going to actually do this. I'm going to raise the board, lift this up, and extend it to the false cases, where P is false cases. Okay. Okay, here we go. So I have this table extended now. I have basically what I wrote above, what I wrote here below earlier, with the 4 T's for P. Now we have a space for the other cases when P is false. So when P is false, we basically repeat this block for the Q and R propositions. So we have double T, double F, and then alternating TF, TF. Okay, great. So now, what about the implication P then R? So false can imply truth, false can imply false, false can imply truth, and false can imply false. So good. What about Q then R? Well, again, this is a usual block, so we're just going to get the usual TF, TT. And then this, well, let's see, P then Q, P or Q is actually only false when they're both false. So these first 2, they're going to be true, but this OR statement is actually false. And you have 2 falses being ORed. Great. So again, what we are assuming to be true are the implications P then R, and if Q then R, and also R itself. So you want to see when these are true. Okay. So when these are assumed to be true, all assumed to be true, this is true. So that checks out. Here, these are also all assumed to be true, and this is also true. Checks out. We saw that already, but now we see new stuff. So here is when they're all assumed to be true, and it's still true. So far it's good. So it seems to be a valid deduction. But here, these 3 are assumed to be true, but this supposed conclusion ends up being false, not true. Notice I'm skipping the ones where these 3 columns are not all true. Like I skipped this one, where this second implication was true, and this one where the first one was true. We would also skip this where these 2 implications are true. And that's because we want to assume all 3 of these are true, but in this last one, this one's false, and in this middle one here, the only true one was the middle, not all of them. But these columns, these 4 columns, are where our assumptions are all true. But the last one here, it's actually a false conclusion. So this is not a valid deduction, actually. So is it valid? No, this is actually invalid. It's invalid deduction. Fantastic. So that actually concludes this video. And in the next video, we'll be taking a look at something a little different. It's still logical, but it will actually involve proving mathematical statements. So that'll be a lot of fun. So I hope to see you all there. Thanks for watching this video, and I'll see you then.